Right, so the next section is on Tehran's theorem. Now, Tehran's theorem is a subsection of the field of extremal graph theory. So very often the question arises, given that a graph doesn't have a particular property, what's the largest size that this graph can have? Now, obviously, if we continuously add edges and we make the graph dense enough, then that particular property that the graph that we don't want the graph to have is going to become inevitable. So the question is, what is that maximum threshold, the size threshold? So to see this, to see an example of this, we pose the following question: how many edges does an n-vertex graph need to guarantee K3 as a subgraph? Now, obviously, if you take the complete graph obviously has a K3. It doesn't matter where you look, it will have a K3. But the complete graph has got all the edges. So obviously we can do better than that. We can start deleting edges. Now the question is, where do you stop deleting edges from the complete graph? And that is equivalent to asking which graphs of order n with no 3-click have maximum size. Now let's look at the 3-click. Now 3-click is an odd cycle. So what would be an example of a graph that will have the largest possible size, where if we add exactly one edge to the graph, we will get a cycle on 3 vertices. Now the logical place to start will be a bipartite graph, because a bipartite graph will never have a C3 or a K3. So observation, a bipartite graph has no 3 cycle. So try a complete bipartite graph to answer this question. So if we look at the order of the graph, let's look at n equals 8. Then there we've got 2 possible drawings of a bipartite graph. Now you'll see that the bipartite graph on the right hand side has got fewer edges than the bipartite graph on the left hand side. So if we distribute the vertices equally or in a balanced way in the 2 partite sets, then we can clearly see that will generate the most amount of edges. So this graph is clearly it's got the property that adding any edge to that graph will give a click on 3 vertices. Okay, so adding any edge there will give immediately a click. If we look at the graph on the left hand side, is the same case there, but it's got way more edges than the graph on the right hand side. Okay, so that should give more or less a clue as to how we would answer this question and how we would find this maximum size. So the maximum size in this case of a graph, one can actually prove it to be this very case here, where if n is even, then the maximum size will be the maximum size there would obviously be n over 2 squared, which is pretty much the size of obviously this bipartite graph. Okay, now if in the case where n is even, we can again then show, in fact, that the maximum size that will be reached will be when the graph is k, the floor of n over 2, and the ceiling of n over 2. Okay. Right, so just an observation here for given in balanced complete bipartite graphs, k n over 2, n over 2, and k minus 1 over 2 and n plus 1 over 2 have maximum size among all bipartite graphs of order n. Now the question, you can go and extend the question now. Let's look at clicks in general. So if this graph denotes or has the maximum number of edges among all graphs with no K3s, is there a similar graph that has no 4 clicks, 5 clicks, and so on and so forth? So can we extend this idea to include clicks on more than 3 vertices? Now, if we look at this following balanced bipartite graph here, just recall that a balanced complete 3-partite graph, in this case, a balanced complete bipartite 3-partite graph containing no 4-click. You can easily observe here that there is no 4-click here, right? So what is a 4-click? It's K4, right? So it's that graph there. Okay, now if you look on inspection there is no, obviously no 4-click there. Right, now for argument's sake, if you add an edge there, right, you can easily see there is your 4-click, right? There's your 4-click. So that graph is definitely adding any edge there is going to give you a 4-click. Okay, so that graph clearly, it's a 3-partite graph. It doesn't contain a 4-click. Now, just a definition here, a complete k-partite graph is a graph whose vertex set is partitioned into k disjoint independent sets so that any 2 vertices in the distinct partite sets are adjacent. Okay, so obviously that's an example of a complete k-partite graph. Now, a complete k-partite graph is balanced if the cardinalities of any 2 partite sets differ by at most 1. So that's just something to keep take a note of. Now, among all complete k-partite graphs of order n, the balanced k-partite graph has maximum size. Right, so I mean, we can see that you can easily see that that if you look at k-partite graphs of order n, if you want to maximize the possible number of vertices, you obviously, or rather, if you want to maximize the number of edges, you want to obviously place as many vertices in each partite set as you can. And that will happen only if you have the balanced variety. So you place as many vertices in each partite set as you can, and that will max out the size of the graph. So that brings us to Tehran's theorem, which states that if you have 2 natural numbers in n and k, and n is at least k, then the balanced bipartite or the balanced complete k-partite graph of order n, that's called the Tehran graph, and that we will denote by T n, k. Now this Tehran graph is going to answer my question, what is the maximum size that a graph can have? And the graph doesn't have a click on, say, k, or it doesn't have a click on k plus 1 vertices. Right, so the answer to that question is in Tehran's theorem. So if we have 2 natural numbers n and k, and n is at least k, then Tnk is that unique graph of order n with no k plus 1 click and maximum size. So rephrasing that, basically it means that if G is a graph that has no k plus 1 click, or in other words doesn't have a complete graph on k plus 1 vertices as a subgraph, then this graph, the edge set of this graph, the number of edges of this graph is at most the number of edges in this to run graph. Okay, so that's the upper bound for the size. That's the maximum size of a k plus 1 click-free graph. All right, and this bound is sharp, meaning that we can find a graph that is k plus 1 click-free, and its size is exactly equal to the size of that to-run graph. Okay, and it happens that we only have equality when the graph is that to-run graph. Okay, so that's the only example of sharpness. That's the only graph that satisfies that, or that gives us equality in that bound there. So that is the to-run graph. That's where we get equality. Right, so how do we prove this? You can prove this by induction. Right, so first we need to establish a base case. So if it's on k, let's look at the smallest value k can take on. If k is 1, then the question now is looking at a graph that does not have K2 as a subgraph. What is the largest size that that graph can have? Now, if you look at a graph that doesn't have a K2, that means the graph can have no edges, right? Because if it has one edge, it has a K2. So basically, this is going to be a graph on, it's going to be a graph on n vertices with no edges, right? So basically, this is the same as Tn comma 1. 1 indicates the partite sets. So your partite set is 1 set, and your number of vertices is n. Okay. So basically, the maximum size, your maximum size of G is pretty much 0, and we get equality with this bound whenever the size of G is equal to the size of Tn1, which it clearly is equal to that. Okay, so basically a theorem is true for k equals 1. So we may assume that the theorem is true, well, we may assume that k is at least 2, and then we assume that the theorem holds for any k prime, where k prime is strictly less than k and bigger than or equal to 2. Okay, so that's my induction assumption. Right, so using the induction assumption, we may then assume that the theorem holds for all cases where the order of my graph n prime is at least k minus 1. Then by the induction assumption, this will be my unique graph that has the required size but is k-click free, and it has largest possible size. Okay, so that is our induction assumption. So now what we do is we take our graph G and we assume that it is k plus 1 click free, and now we need to prove that its size is at most that, and equality only occurs when G is in fact that graph there. Right, so we assume G to be k plus 1 click free, and what we do is we take G and we choose G to have the largest possible size. And the aim of that, choosing it that way, is, remember, we want to end up showing then that G is in fact this graph T in K, the Tehran graph. So now go to G and we select V to be the vertex of maximum degree, delta of G, and let's check, look at the graph induced by the vertex, the open neighborhood of V. Right, so there we've got a little diagram. This is V's open neighborhood, which is H, and there we've got the vertex set of V minus the set H, which is this whole, which is that whole section there. Okay. Now it's obvious that the graph H, which is the open neighborhood, the subgraph induced by the vertices of the open neighborhood of V, that graph has no K click. So this means that there's no complete graph within H on K vertices, because if there was, then obviously, if there was a click, then let's call this click, let this graph be a K click, right? Then obviously, if there was such a K click within the open neighborhood of H, then obviously what's that going to give me? That is going to give me a K click plus V, which is a K plus 1 click. And that whole thing there is a K plus 1 click, which is impossible because we said G is K plus 1 click free. So therefore, by the induction hypothesis, because this graph is click free, we have, and because H has right, so by the induction hypothesis, the number of edges in the graph H is at most the number of edges of this Tehran graph, which is a Tehran graph, delta comma K minus 1. Alright, so before we continue, I just want to make a point there, detail that's omitted. If we apply the induction assumption to H when delta is at least K minus 1. Now, if delta is at most K minus 2, the argument for the rest that we're going to follow for the rest of the proof now also can be used for this case without it being very different. So what you're going to do is you're just going to note that the cardinality of the edge set of H, that will be at most the edge set of the graph T delta comma delta, and T delta comma delta is going to be a complete graph because it's a graph on delta vertices with delta Bipartite sets. And that you can just write that delta, you can write that as, you can replace the delta there with K minus I, where I is an integer, bigger than or equal to 0, or bigger than or equal to 2. And it's going to go up until K minus 1. Right, so in that particular case, again, we will then eventually show that the size of G is going to be bounded by the size of this graph, right? It's still going to be the same. Right, so for this case. For this case, we're going to show that the size of G is in fact the same as the size of that, and also the same argument can be used in that case. We're going to show that the size of G is essentially bounded by the size of that graph. And the size of the size of this graph is less than or equal to the size of that graph there. Right, so essentially we're not going to look at this case. That you can look at that separately. We are just going to look at that case. Right, now applying that induction assumption, we have equality if and only if H is in fact that to-run graph. So so now what we do is we define a new graph, and we've defined this graph by taking T delta K minus 1, which is that graph there, and we take N minus delta isolates, and we look at the graph, the plus between the two. We add the two graphs together, meaning that we join every vertex in this set of vertices to every vertex there. Now it's important to note that G prime does not have a K plus 1 clique. Right, now look, this graph cannot have a K plus 1 clique. Right, so if there was a K plus 1 clique, then it can't only lie in this section, that we looked at. It can't lie only in that section, so it's gonna lie possibly there. Okay. Now, if it includes two vertices there, you're going to see that can't be a K plus 1 clique. Right, so it can include at most one vertex there, and it could include all the vertices there, right? Now, again, this section here cannot have a remember we said it doesn't have a K clique. Right, and if it doesn't have a K clique, then just adding one vertex to it, it's not going to, taking that one vertex there and joining it to all the vertices there, that's not going to produce a K plus 1 clique. Right, so again, so what we do is we claim that in fact we've got equality there, and G reaches its maximum size. So again, recall that the degree of each vertex in G is at most delta, and for each vertex W in the vertex set of G minus the vertex set of H. So what they're talking about there is, I mean, that's obvious. Every vertex there is going to have, including that vertex there, is going to have degree at most maximum degree. All right, that's obvious. Right, so the size of G is going to be the size of H, okay, plus, now, or it's going to be at most the size of H plus, what we're going to do is we're going to count edges. So we're going to sum over the degree sequence. So we're counting edges there. We're going to count each edge at least once. Right, and that is at most that. And we reach the maximum value there when each vertex has its maximum degree. And again, this edge set of H, cardinality of that is bounded by that quantity there from previous notes, and that still stays the same, and that is equal to the size of G prime. I remember we said that we chose G to be a graph that's K plus 1 clique free, but it has the largest possible size, and therefore the size of G must be at least the size of G prime, because G prime is K plus 1 clique free. Right, so therefore this is going to imply the fact that the size of G is at most the size of G prime, and vice versa. Right, so obviously that's going to imply that the size of G is going to be exactly equal to the size of G prime. Okay, So therefore, that's going to force equality there. So what's going to be the implication? It's going to mean that every vertex in W must have maximum degree. Okay, it's going to mean that the size of the graph H must be exactly equal to that, the size of the Tehran graph T delta K minus 1. It's also going to mean that this set of vertices here must be a independent set, because if it was not the case, if there was an edge there for argument's sake, then in this sum here we would basically count that edge twice, and therefore that's going to mean that we can in fact make this whole sum here, we can make it smaller by at least 1, and you're not going to get equality between that and that there. Okay, so so that's going to force the three things I mentioned. Right, so therefore H, by the induction hypothesis, H must be T delta K minus 1. Right, so H is going to be a complete K minus 1 partite graph. Each vertex in VG minus VH must have a degree delta, and this set of vertices is going to be an independent set, because if it's not the case, then again we can make this, we can basically, in the original proof, we can just replace this with this whole term here minus 1, and then we don't have equality. Right, so putting everything back together, so because H is a K minus 1 partite graph, right, so again we said because H is a K minus 1 partite graph, the remaining vertex set V minus H is independent, so basically V is adjacent to every vertex in that partite set there, and all those partite sets. Okay, and each vertex there is going to be adjacent to all the partite sets. So basically, what this is going to imply is that we have H, which is the K minus 1 partite graph, and then we form the graph G by adding an extra partite set. Okay, and the partite set in this case, the extra partite set, is going to be the partite set, the purple partite set, which is this, which is that partite set there. Okay, so this is going to be a new graph. It's going to be a graph, or it's going to be a graph that is going to have, it's going to be the graph T in. We had K minus 1 partite sets, and we're adding an extra partite set, so that's T in K. All right, and the graph G is that unique graph T in K that reaches the maximum size. Okay, so a typical question in extremal graph theory is how many edges do we need in a graph of order n to guarantee a certain type of subgraph? Now, the corollary from Tehran is every graph of order n with at least that many edges plus 1 will definitely contain a K plus 1 clique. So if it's got one more edge than the Tehran graph has, then it will have a K plus 1 clique. So I mean, you can now extend this to other substructures. For example, you can ask yourself, how many edges does a graph G of order n need to guarantee a cycle? To answer that, that's pretty simple. We need at least n edges. And then also, how many edges do I need to have two distinct cycles? The answer is n plus 1. N plus 1 edges. We can choose the graph. We can look at graphs that don't have any cycles and that have the maximum possible edges, and that will occur when the graph is a tree. And then adding any edge is going to give me a cycle, and then adding another edge will give me two distinct cycles. Now let's extend this let's make it even more interesting. Let's require the two cycles to be disjoint. In other words, they're not allowed to share any vertices or edges, and that brings us to the next theorem. This theorem states that if G is a graph of order at least 6, and it has at least 3 times its order minus 5 edges, then it will definitely contain 2 vertex disjoint cycles. Right, so that's the requirement of the size that we need to guarantee 2 vertex disjoint cycles. So the maximum size of a graph without 2 vertex disjoint cycles, the maximum size will be 3n minus 6. So I mean, this is very much like Tehran's theorem, and you can actually ask any type of question that you want in this case. You can include other structures as well. Now, what it suffices to show that every graph of order n at least 6 and size exactly 3n minus 5 has 2 disjoint cycles, and we'll employ induction on n. Right, so if n is 6, then the graph has got 3n minus 5 equals 13 edges, which is 6 combination 2 minus 2, and that's pretty much the graph K6 with 2 edges removed. So either the 2 edges are incident with the same vertex, or they are disjoint. In the case where they're disjoint, right, so there's my first cycle. And right, the other cycle we've got there. Okay, and in the second case, we've got a cycle there, and we've got a cycle there. Okay, so obviously we've got 2 disjoint cycles. Now, so we may assume n is at least 7. So just an idea, if we can alter G to obtain a graph G prime with 1 vertex and 3 edges less than G, then obviously by induction G prime will have 2 disjoint cycles. And then we just need to show that if G prime has 2 disjoint cycles, then we can modify G prime again to get G, and just make sure that we use the fact that G prime has got 2 cycles, 2 disjoint cycles, to construct 2 disjoint cycles in G. Now it's important to note that the minimum degree of G must be at most 5. If this was not the case, right, then we would have that the sum of the degree sequences will be at least 6n, and that will imply that 2m is at least 6n, which will then imply that m is at least 3n, which is strictly bigger than 3n minus 5. Okay, and we assumed that the graph G has exactly 3n minus 5 edges. Just please note that, again, we're assuming that G has exactly 3n minus 5 edges, because if it has more than that number of edges, again, we can we can apply induction on the number of we can pretty much apply induction on the number of the order of n plus the number of edges. So making any one of n, either n or m smaller, will produce a will produce a desired result. So if we have more than 3n minus 5 edges, we can just remove an edge and apply the induction assumption. Okay, so basically, so the minimum degree of G must be at most 5. Right, so we've got that this we have that the sum of the degree the sum of degree sequences is 6n minus 10. So it's pretty much that quantity multiplied by 2. And okay, obviously now that implies that yeah, it implies that little thing we noticed there. So now we're going to take a minimum degree vertex, and we're going to play around with the minimum degree vertex. So let V be a vertex of minimum degree, and let V1, V2 up until wherever, let those vertices be the neighbors. So we look at some cases. We're first going to look at the case where the degree of V0 is at most 3. Okay, now if it's at most 3, let's delete G. Let's from G delete V0 and the edges incident with that vertex. So we're deleting right, so we're deleting at the very worst, we're deleting 3 edges, right? So the size of this new graph is going to be at least 3n minus 5 minus 3, which is 3n minus 1 minus 5. And we can apply the induction assumption on G prime, which is the graph G that I take the vertex V0 away. Right, so obviously the graph G prime is going to contain 2 disjoint cycles by induction, and so G will also have 2 disjoint cycles. Right, the next case is where the degree of V0 is exactly 4. Right, so let's assume first that the graph induced by the open neighborhood of V0 is not complete. Right, so there's at least one edge missing. Now what I do is I construct the graph G prime by deleting V0 and adding the artificial edge V1, V2. Right, so again, this is how I construct the graph, right? So what I do is I delete that vertex V0 and I join V1 and V2. Because remember, we assumed this subgraph here is not complete, so there's at least one missing edge. Now, by the induction assumption, let's just first check that this graph has got the required number of edges. So this graph is going to have n minus 1 vertices, and it's going to have 3n minus 5 edges, and from that I'm going to subtract 4. But I'm going to add 1, so I'm subtracting 3. Okay, so again, that thing, sorry, that's a typing error, that should be minus. Okay, so it's got the required number of edges, and so by induction, the graph is going to have 2 disjoint cycles, C1 and C2. Right, so there are my 2 disjoint cycles. Now let's just see what happens here. If C1 could possibly share a vertex V1 or V2, right? That won't be a problem. However, the problem comes in when either C1 or C2, say C2, shares has this edge. Or rather, Is the problem scenario, right? That's the problem scenario. The problem scenario where this cycle shares one vertex there, or shares both those vertices there. Well, in this case, you will have, say, that situation there, okay? Okay, so what do we do in that situation? Well, all we do is we take the original vertex that we deleted, which is V0, and we just go and add it back, right? So there it's going to look like that. Okay, so basically the graph G is going to have two disjoint cycles, and the two disjoint cycles now are going to be the blue cycle and this new cycle, which is going to include that whole section there. Okay, so the graph is going to have two disjoint cycles. Okay, so that is what they say, that's what they're talking about there. Okay, so now what we need to do is we need to look at the case where the graph induced by the vertices in the open neighborhood of V0 is complete. Now, if a vertex W in the vertex set of G without the closed neighborhood of V0 has two or more neighbors in the open neighborhood of V0, right, then the closed neighborhood of V0 union W induces a graph with two disjoint cycles. Okay, so why is that? Let's just look at that. Let's look at a diagram. Right, so again, what they're saying there is if this vertex W is got. Remember now, we assumed that the open neighborhood of V0 is a complete graph. Now, if there's a vertex, this is the set V of G minus the closed neighborhood of V0. Okay. Now, if there's a vertex W that's adjacent to two vertices in the open neighborhood of V0, then the graph is going to have two disjoint cycles. And why is that? Well, look at it this way. There you go. That's one cycle. Okay, and the other cycle, you can do this, you can do that, you can do that, you can do that. Okay, so it's got two disjoint cycles. So obviously, then we're done. So we basically may assume that every vertex in that set there, has at most one neighbor in the open neighborhood of V0. Okay, so that has to happen there. It can't have two or more neighbors. Right, so we may assume that no vertex in that set has more than one neighbor in the closed neighborhood of V0. Right, so basically the number of edges between these two sets, that set and the closed neighborhood of V0. The number of edges between those two sets is at most n minus 5. You can easily see that, right? So this set has got cardinality n minus 5. And there's at most, for each one of those vertices, there's at most one edge that goes that way. Okay, right, so it's easy to see that. Right, so now what we're going to do is we're going to construct the following graph G double prime. And this graph is you're going to take G and you're going to delete V0 and two of these neighbors. Right, then the resulting graph is the size is going to be 3n minus 5. How many edges are you deleting? You at the very worst, you are deleting. Right, so you're pretty much essentially deleting this little triangle. Okay, so we need to just count how many edges are we deleting. So at the very worst, okay, so we're deleting these 3 edges. Okay, so we're deleting -3. We could possibly be deleting, right, so again, we're deleting those 2 edges there, so that's -2. We're deleting those 2 edges, so that's going to be -2. And we are deleting those 2 edges there. Okay, so that's another -2. So in total, we are deleting -9 edges so far. Okay. Now, again, we have to take into account edges that run that way. And at the very worst, every vertex there that is in this particular set here could be adjacent to a single vertex in the set V1, V2. Okay, remember you can't have that. We just said that can't happen. Okay, so you are deleting at the very worst a further n-5 edges. Okay, so in total we are deleting 9 plus n-5. Okay, so that becomes that. So that is 2n-9. And 2n-9 is at least the order of G double prime. Okay, so this is going to imply that G double prime must have a cycle. Remember, a graph that's got of order n, if it has n edges, it's going to have a cycle. This cycle and the triangle V0, V1, V2 are disjoint cycles of G, okay, which completes the proof. Right, so we need to consider the final case, and that is the case where the degree of V0 is 5. Right, now if the subgraph induced by the closed neighborhood of V0 has at least 13 edges, then by the case n equals 6, there exists 2 disjoint triangles in the closed neighborhood of V0. So we may assume that this graph is at most 12 edges. Right, so this is going to imply that at least one neighbor, V2 say, is non-adjacent to at least 2 other neighbors, V1 and V3 say. Right, so there we've got our sketch. So what I'm doing now is V2 is non-adjacent to V3 and V1. So what I'm going to do is I'm going to join V2 to V3 and V2 to V1. And then I'm going to delete. We're going to delete V0 and all the edges incident with it. Right, so essentially I am taking the size, and what I'm deleting is I'm taking 5 edges away and I'm adding 2 edges. So I'm only essentially deleting 3, and that becomes 3n-1 minus 5. And by the induction assumption, this new graph contains 2 disjoint cycles. Right, so there are my 2 disjoint cycles. Now, we can certainly not have that. We can't have that and the following. Can't have that and say that as an example, because then the 2 cycles is going to share It's going to share that vertex there. So obviously that can't happen. Okay. So at the very worst, if neither C1 nor C2 shares any of those vertices, then we are done. Okay. So the only problem case arises where we've got, say, this that happens. Okay. Right, so that happens. Okay, so we've got that situation there. Well, in that case, again, that's not so much of a problem because we can revert back to G by just replacing the vertex V0, or rather adding the vertex V0 back again. And you're going to have this situation here. And again, you're going to just add that and form a new cycle. Okay, and your graph G is going to have the two disjoint cycles, the blue and the purple cycle. Okay, so that completes the proof of this theorem. Right, now this example shows that this result is actually best possible because here we show that there's a graph that's got 3n minus 6 edges, but it doesn't have two disjoint cycles. Okay, so again, this example here, another question arises: how many edges in a graph guarantees a subgraph of minimum degree k? Now, the previous example, that graph, it has no subgraph of minimum degree 4. More general, if you look at the complete graph K on K minus 1 vertices, and you add that to a set of n minus K plus 1 isolates, that has no subgraph of degree K. And if you go and count the number of edges of this particular graph, it adds up to K minus 1 n minus K choose 2. Right, so there we've got that set of isolates, and how we construct this graph. Again, we just go and join, we can add all these edges here, and you can go and count the number of edges there, and it's clear that it is the quantity that we are looking at. Now again, this graph does not have a subgraph of minimum degree k. And one can easily see that subgraph minimum degree k is going to have to contain at least one of those vertices there, because that's a minimum degree vertex, and I mean none of those vertices have degree k. Okay, now it turns out this theorem gives me a lower bound for the size. Okay, it says that if G has order n, and the size of this graph has at least so many edges, so it's pretty much it's that cardinality plus 1, then the graph is going to have a subgraph minimum degree k. So again here, if you go back here, you can see here, as soon as you add an edge there, you have a subgraph of minimum degree k. So that graph definitely exceeding that amount of edges will give you the desired result. Okay, so I'm going to, again, this is a proof that you guys can go and work through on your own. It's very similar to the previous proof, but much shorter. You just employ induction on n. Now n must be at least k plus 1 if you are to have a subgraph of minimum degree k. Alright, so we need to first establish it for the base case, and then assume n is bigger than or equal to k plus 2. All right, so the proof has got two cases: the case where delta G is at most k minus 1, and the case where delta G is at least k is bigger than k minus 1. All right, so that concludes this section on extremal